Olá, Data Science Portugal. É grande prazer estar aqui com vocês, even if it is in these very odd circumstances of us all being completely remote. I'm a researcher at Google Brain, and today I'll be talking about a question that I find really interesting, which is how do models learn? In general, a little bit of background about me. My research agenda is focused on how do we train models that fulfill multiple criteria? So not just high tested accuracy, high top-line metrics, but compact, so works in resource-constrained environments, fair, model interpretability, and robust to distribution shift. Today, we'll be talking about one of the most interesting topics I've devoted research to, which is how do we understand feature importance in image classification models. In these brief 30 minutes that we have together, I'm hoping to firstly give you some context for why we want to do this. So what is motivating going beyond tested accuracy? And what are some of the popular interpretability tools and research directions for deep neural networks? And secondly, I do want to touch on what some common misconceptions are about interpretability in deep neural networks. Finally, perhaps the area I'm most excited to touch on is some of the open questions. So what are researchers thinking about in this field, and what are interesting future directions of research? I'll be discussing past and ongoing work with my lovely colleagues. And to start with, I'd actually like to talk about a story. And the story is about a horse called Hans, who was quite famous in Berlin between 1891 and 1907. And Hans the horse was famous because Hans demonstrated a remarkable ability to give the correct answer when asked to estimate the size of a crowd, asked to answer some simple arithmetic functions, or to identify colors. Very naturally, this was quite confusing for everyone involved. How was Hans the horse showing this type of high accuracy? And the answer was only revealed in 1907. A fairly clever experiment was designed where the human who asked Hans the question did not know the answer. And in this setting, where the human didn't know the answer, Hans also did not know the answer. In fact, what had happened is that Hans was simply picking up on microscopic facial clues in order to get the right answer. This notion of high accuracy without true learning is actually very prevalent in modern machine learning systems, particularly ones that are considered black box, like deep neural networks. So deep neural networks have resulted in a huge leap forward in top-line performance on image classification tasks. And today we'll be mainly talking about image classification, which is where you're trying to identify and classify a single object. And in many ways, the most dramatic switch in performance regime occurred in 2012. And in 2012, AlexNet was proposed. Prior to AlexNet, a lot of emphasis had been on hand-coded feature engineering, so quite complex functions, but that were completely specified. And so it was very clear what features were being extracted. The image here is of the SIFT algorithm, but in fact, there's also great examples like the Soba edge filter and the hog filter. And the benefit with these were very interpretable. Because the function is explicitly stated, the mapping is interpretable, but there's difficulty generalizing well beyond a few narrow tasks. And in 2012, AlexNet swept the board with the competition, and everyone defaulted to using convolutional neural networks. Of course, the reason why was that instead of explicitly specifying what features to extract, the model learns what features are important for the task through feedback, minimizing the loss through backpropagation. So we give up full specification of the model. And this is often why deep neural networks are termed black box, because it's difficult to specify why a model made a certain prediction. And delegating full learning of the representation to the model has and can lead to clever hands moments. So these are 4 images. So 2 are images that the model predicts correctly, and 2 are images that the model predicts incorrectly. So some of you may have already intuited the answer to this question, but that lovely picture of a cow on the Alpine Hills and the picture of a limousine in the parking lot, those are examples that the model does predict correctly. And the example of the cow meandering on the beach, as well as the example of the limo on the snow, are examples that the model predicts incorrectly. Why? I think perhaps you've already jumped ahead, but in many ways it's because the training data that these models are trained on has more cows on these alpine beautiful settings than it does cows on beaches. So this is a difference in terms of performance that humans are surprisingly robust to. In fact, we can still identify an object despite it being in a different background. But deep neural networks are particularly sensitive to this type of spurious correlation with unrelated features. And it's an example of high accuracy without true learning. Here's another example. This is a Microsoft API, and it's generating a caption for an image. So on the left, you have an image of verdant hills that's tagged sheep. And on the right, you have an image of two children holding sheep that's been tagged dog, presumably because most images in the training set of children holding animals in this position were of dog. This may seem comical or interesting, but it matters when clever hens moments happen in sensitive domains, and this is where there can be a huge cost to human welfare. Here's two examples from the healthcare space. So in the first one, researchers realized that photographs of malignant skin lesions were often photographed alongside a ruler. So the model learned to default to where the pictures had a ruler to give a certain classification. On the right, classification of pneumonia, it was realized that certain hospitals would place metal tags on the patient, and the location of the tag would actually be based upon the severity of the condition. And so the model defaulted to that proxy variable in order to make a classification. And there's also examples of how parametric models often have a disparate impact on underrepresented instances or attributes. And this often is becomes a fairness concern, particularly when, because many fairness questions are concerned with the long tail. So it's an underrepresented protected attribute in the long tail. All this to say, and all these examples to say, is that top-line metrics often hide critical model behavior. And often we need interpretability tools to order and understand model behavior. What are these tools, and what are some common research directions? I think part of the fun of this type of talk and having a broad audience is also just sharing some of the research today that has been of interest. And one of the first ones is model distillation. And here the objective is to take a large model, which may not be perceived as interpretable, and to distill that representation to a smaller model, typically, which is perceived to be more interpretable. So an example might be distilling a deep neural network into a decision tree. The difficulty with this research direction is that it's been shown to be quite difficult to compete in terms of accuracy, so you do compromise on overall accuracy. A second research direction is visualization tools. And visualization tools typically are concerned with projecting high-dimensional spaces into dimensional spaces that are more intuitive for humans. So as humans, we tend to do quite poorly if the number of dimensions scales past 2. We can deal with 3, but beyond that, it becomes a little tricky. And so tools like t-SNE, visualizing the loss landscape techniques, are concerned with essentially bringing these high dimensional spaces back into dimensions that we can comprehend. 3 is quite fun because we actually don't think of this typically as interpretability, but I think it's actually one of the most valuable tools we have to understand the decision boundary that the model learns. So this is one example of agent-based exploration. It's a work from OpenAI, and in it, the agents learn to perform a task. And you see the frames as the agents learn and interact with the environment. And what's interesting about this is it gives great insight into the decision boundary that's learned by the model. And also, it naturally structures the data from easier to harder, because you see as the model becomes better, you see what data it selects and what actions it takes to engage with its environment that are more useful. And this is actually a really important question within machine learning, because a lot of what is interesting is how should we structure data to understand the relative difficulty? How can we understand what the model finds difficult? The fourth, which I'll talk about more today because it has been a topic of particular interest for my research, is how do we estimate feature importance? And in fact, there's three main directions within this. So one is local feature importance, global, and weights and activations. So local feature importance is very concerned with estimating the feature importance of the attributes in a single data example to a single model prediction. So it's interesting explaining model behavior for a single example. And in fact, much of this has been motivated in part by the high dimensionality of the input space. So a lot of research is focused on local feature importance because it's very hard to do global. In fact, it's tricky because scaling over massive data sets, when each data has in many natural image data sets, 250,000 features is seen to be computationally infeasible. But global feature importance is really interesting, and I'll cover some of this in my later discussion of what is interesting to think about next. And this is actually recent work that I did with a collaborator, and in fact, this is trying to show what examples does a model find challenging or easy to learn. And here, this is estimating example difficulty using variance of gradients. And the examples on the left are low variance of gradients, so they're easier for the model to learn. And the examples on the right are higher. And getting this relative interclass ranking can be quite useful for interpretability domain experts in order to understand where they should pay attention, what needs further downstream data auditing, and how to do mitigation strategies. The third is weights and activations. And this is a really interesting area because there's still many open questions here. Largely, this has been devoted to estimating the role importance of individual neurons or weights. So this may have come across before as discussion of a kitty filter, whether a filter is very responsive to a particular trait or to a particular class. This is interesting because there's been contradictory results, and so it remains an open question. While some work suggests that there's selectivity, that there's such a thing as perhaps a kitty filter, other kitty neuron, other work suggests that, in fact, with modern networks, particularly with regularization like batch norm, you do not see such a specialization. In fact, that there tends to be much more diffuse feature extraction. And so this is always fun when there's a question mark, because it means more work needs to be done in this area and more interesting findings to come. I wanted to talk, as part of this talk, about misconceptions about interpretability, mainly because interpretability is often discussed as a desirable property, but in those discussions often lacks nuance in terms of what do we mean by interpretability and how do we measure progress. And that's in many ways misconception one, which is that a model is either interpretable or it's not. You may have heard this variant of this as we need all models to be interpretable, or this model is not interpretable, it's a black box. And the truth is that interpretability is not a binary attribute. It's very rare that we will sign off on a model as 100% interpretable. And measuring progress towards a model being interpretable is also challenging, since there's no real finish line, and it's hard to articulate progress as we made this model 30% more interpretable today. In fact, much of the discussion around interpretability has to be around who is the end user. Misconception two is that we need all models to be interpretable. So kind of like any desirable property, the weight that we place upon it will depend upon a few factors. In the same way that we may emphasize more model compression if we're in a very resource-constrained environment, we may emphasize interpretability if we have a certain combination of factors. And I describe some factors here. So one is whether it's a sensitive domain. Are you deploying a model to a domain like healthcare, facial recognition, self-driving cars, and hiring. I was trying to think of the last one. But these are typically ones that come to mind because in many ways the trait there is that an incorrect prediction can adversely impact human welfare. And then the second is, does this trade off with other model desiderata? So by optimizing for interpretability, are you compromising some other notion that you care about, such as guaranteeing privacy? A common example of this is that I've often been asked previous talks whether the model weights should just be released to the public as a means of auditing what the model has learned. But in many ways, this may compromise the expectation of individual user privacy, because it's quite possible, and recent research has shown that you can discern what the training data is by under certain circumstances looking at the weights. And so there has to be a notion of what you're trading off and what your overall requirements are in the auditing process. The third is historical performance. So is historical data of the model behavior in different test conditions limited? If this is the case, there's going to be more emphasis on auditing model behavior. However, if you have a lot of historical data over a longitudinal period in many different test set conditions, so many different deployment conditions, you're probably going to place less emphasis on interpretability because you already have enough input-output combinations to have an understanding of what the model decision boundary is like. And you may have sufficient trust that you don't need to do additional auditing. Misconception 3 is actually something I've spent quite a bit of my research on, and it's that meaningful explanations are reliable. I've done quite a bit of research to show that this is not the case. So explanation may be meaningful to a human, but not be faithful to a model. We may trust the explanation, but it may not actually be correct. So I did work the reliability of standard methods, a benchmark for interpretability methods of deep neural networks, and both in essence show slightly different things. But the first is that you can add a small corruption to the input, and that cannot impact the model. So the model is unchanged by that input transformation, but the explanation is sensitive to it, which should not be the case. And once you know that, you can actually purposefully corrupt the explanation. So here, with a little kitty cat, we showed that example. Misconception 4 is that interpretability methods should align with human judgment. I actually have an example of this. So I think that in many ways, the imposition that models should extract features in the same way that we do kind of misses the point. These models are, because of their very definition, they're not our visual system. And so diverging from human judgment does not mean the model behavior is incorrect. In fact, in retinopathy studies, it has been shown that convolutional neural networks can extract features that humans simply cannot, like discerning the gender, the cardiovascular risk, and whether an individual smokes, just from the image of the retina alone. And this is perhaps intuitive because convolutional neural networks are taking advantage of pixel-wise differences that we simply can't because of our log-scale vision. And another example that I do like to mention is that even things like AlphaGo, often expert players in Go will watch these games to learn a new way or technique of playing the game. So imposing the criteria that our models and thus our explanation should align with human judgment isn't a sensible assumption. And it may be the case that we can actually learn from where explanations diverge. Misconception 5 is that there's one interpretability tool to run them all, rule them all. And really, the criteria for what is interpretable will depend upon our vantage point and downstream tasks. So this is an example I always like to give. So back in the day when we were nimble and could fly, you may have been on a plane and you may have heard the words plane delayed due to additional safety checks. And that was probably very different from the conversation happening between the pilot and the ground crew. Perhaps the ground crew said to the pilot, pitot tube 316DA is out. And then the pilot said to the co-pilot, airspeed sensor is out. And then the co-pilot finally reported back. And in fact, all those explanations may have been sufficient, even though they were dramatically different. And the reason why is that really a good explanation of behavior is one that is suited to what is an actionable downstream task. And the final is that interpretability is the same as fairness. They're not the same. In fact, interpretability can help inform accountability, but it's not the same. You can use it as a tool, but having an interpretable model does not guarantee that it's fair. I now want to talk a little bit about what I think are important open questions within interpretability. These are kind of questions that I'm currently thinking about, that some of my colleagues are thinking about. But one is, how do we understand how feature importance forms over the course of training? So most interpretability techniques and most research to date on interpretability take as a starting point a trained model. And in some ways, if you think about it, this is an odd assumption. Because a model, a particularly deep neural network, has been optimized explicitly with only a cross-entropy loss to minimize. And there's no part of that constraint that ensures that it would be interpretable. And then afterwards, after the weights are trained, we do acrobatics to make it interpretable. But understanding how feature importance emerges over the course of training is one of the most important steps in understanding if we can explicitly optimize for more interpretable models. This is also interesting because very recently research has emerged showing that there's clear, distinct stages to training. So one paper by colleagues at Google showed that in the first parts of training, the easy mode examples are learned, and then in the latter parts, the memorized examples are learned. And these tend to be atypical or rare. Another really fascinating paper shows that really there's critical learning periods. So if you show a model corrupted data in early stages of training and then normal data in latter, it's actually not able to converge back to the same performance. And this is recent work that I did, and it's really also trying to get at that. And I did it with my collaborator, Chirag, and in what we ask, what is the average variance in gradients over the course of training? And the hypothesis here was that if an example is easy, it will converge to a narrow range early in training because the gradients will stabilize, the model is placed on the decision boundary, and so you would expect the variance to be low. If the example is challenging, you would expect the gradient to oscillate a lot more over the course of training because the model is trying to place in the decision boundary and is not finding the right place to place it. And what we show is that, in fact, there's very distinct semantic clusters that form when you compute fog or variance of gradients. And for example, here, we see with cars, we see that the low variance is uncluttered backgrounds, high variance are these very cluttered backgrounds, but also much more atypical cars. So you see here in row 2, these are antique cars here and here. So it's interesting. These are perhaps more challenging for the model because it's an older maker car and it's out of distribution. We even show that it appears to capture a color bias present in the network. And this is interesting because it tells us something about how we rank relative importance, but also the stages of training. We show that VOG is an effective ranking, so it discriminates easily between easy and challenging examples. This is CFAR 100, and this is a percentile score. And we show that for examples with high VOG scores, so over the 90th percentile, these are much harder for the model to classify. The second direction I'd really like to talk about is optimizing explicitly for interpretable models. So I mentioned this before, but moving away from taking a static, the endpoint, and then optimizing explicitly for whatever notion of interpretability we may want to articulate. For example, there's been very little research in this direction, but one paper I enjoy is looking at if adversarial robustness improves the perceptual quality of the gradients. So regularizing, some of the regularizers used to make networks more robust lend perceptual quality properties to the gradient heat maps that are heavily used for those saliency methods. And if this is something we want, perhaps we just want to optimize for it explicitly. The direction three is focusing on the relative importance of features and not just local. So interpretability methods like saliency maps are inherently local. And I mentioned this before, but this is being driven in part by a high dimensional input space, which makes it very computationally difficult to scale saliency map type estimates across the data set. But there's very interesting work on how we do a more computationally efficient ranking. So even variance of gradients, which I introduced before, is an interesting way to try and get a useful ranking across a class of the most challenging and easiest examples. Really, the other shortcoming of saliency maps is what happens next? So, okay, so you have the saliency map for an image. In this case, it was a sandwich. So do you then, is this a good saliency map? Is it a bad saliency map? Do you have to inspect more saliency maps to make a decision? Data sets that are modern are very large. So would you have to look at all examples in the test set? And human understanding tends to be relative. So understanding a relative distribution of what the model perceives as challenging, easy, aids interpretability. This is a recent work that I also collaborated on with wonderful colleagues. And this is where we try and get at this relative importance by comparing models that have been trained to different levels of compression. And we classify as pre-identified exemplars these examples with a high level of divergence. And you can see here that this is a fairly typical plastic bag. This is tagged plastic bag, despite it being perhaps a very unusual setting for a plastic bag. Same with toilet seat and espresso. So these pre-identified examples tend to be much more rare, atypical, and thus surface to a human orator some of the examples that merit inspection, further annotation. We validate that by actually showing that they're more challenging for both humans and algorithms through a human study. And this and other kind of relative measures of the distribution that surface what is estimated to be the most challenging or the easiest help provide a tractable workflow for human-in-the-loop learning. And it really helps aid downstream tasks of auditing or doing further data cleaning or isolating a subset for relabeling. And I want to say a few final thoughts. So really in this talk, I hope to do a few things. I share with you some examples of what motivates this focus on interpretability tools, which help serve to audit unexpected behavior and proactively and retroactively identify points of failures in our model behavior. And then I talked about what are some of the common interpretability methods and directions that a lot of research attention has gone into. I also talked about some of the misconceptions. How is the word interpretability used in a way that doesn't have precision? How can we be more precise about how we talk about this subfield? And finally, I talked about some of the open questions that I'm really interested in, such as how do we understand how features emerge over the course of training, explicitly optimizing for interpretability, and ordering tools that surface relative importance rather than focus solely on local estimates. I'm really happy to chat about all these. And I believe I'm probably somewhere right now waiting to answer any questions that you may have. So thank you again, muito obrigada, and I'm very delighted to stick around and answer questions, as well as more general questions you may have about the fields of model compression, interpretability, and robustness.
Hey everyone, we're back from Sarah's talk. I would like to throw out a really big thank you for this presentation. By the way, fun fact about Sarah, I have to confess, she has lived in one of the southernmost countries in the world. And also, so now you got to draw like a Venn diagram, and also in two enclaves of that same country. Okay, so if you're into like reading maps while your models run, you have a challenge right here. Okay, however, the price is just geography street cred, so with a grain of salt. Okay, Sarah is now joining us for the Q&A. We'll be reading directly from the questions you have posted online based on the number of votes. You know the drill. Sarah, are you there?
I'm here. Can you hear me?
Yes, I can. So I guess that's good enough.
That should be good enough. Lovely to be here. So will we reveal the correct answer to the geography question at the end, or just...
I don't know. You know what? Like we have a badge challenge going on, and that's not one of the questions. But I guess in the end we can reveal it. We'll see. We'll see
Okay,
what goes
sounds
on.
good. Just in case people are waiting, looking at their maps right now.
Yeah. Okay. Yeah. No. I guess. Okay, guys, come back from the map. Pay attention to this, and then go back to the map. Okay. Let me see if I have okay. I have a question here. Sarah, first question is, do you think that interpretability effort will overtake performance effort in the sense that people will focus more on trying to find the reasons behind the model behavior instead of focusing on choosing the right model and right parameters? I think this is a long question. Should I repeat? No.
No, that's okay.
Okay.
I mean, it's an interesting question because there's a few elements there. This idea that we may care less about accuracy and care more about interpretability in certain settings, and definitely settings. So healthcare, facial recognition, all these very sensitive settings where human welfare can be impacted. There's kind of a broader question there, which is perhaps let's set those sensitive domains to the side for a second. Will we just want to learn more about our models? And I think here it really depends upon the perspective of who's looking at the model. So researchers right now are definitely in a stage of renewed interest in interpretability. So a lot of the interpretability tools we use today actually originated because researchers couldn't tell why the models weren't training properly. And here again, in this moment in time, we see researchers struggling to understand why their models fail in such unexpected ways when they deploy. And so there's renewed interest in let's have auditing tools to understand where does our model actually do well and where does it do badly. On the consumer side, I'm guessing there's also a lot of work to be done because consumers want to have a sense of not only why a model made a prediction for their data point, but they want to know how they compare. Like, is the prediction for them worse compared to other people with their same attributes? And so there's a renewed focus on auditing. How does that trade off against test set accuracy? That depends on the use case. So I work in model compression as well. And in model compression, people are surprisingly willing in real world scenarios. So there's research where researchers are all about, let me increase test set accuracy by 0.5%. Let me get a little bit more. And in the real world, when you're working in an applied domain, 0.5% means nothing. You're willing to compromise on a level of test set accuracy in order to make sure that your model can be deployed to resource constraint. And I think it's the same for interpretability. It depends the degree of the trade-off. And part of the issue now is that because we do interpretability separate from the model, we actually end up not being able to articulate that trade-off. So I think an exciting direction is let's optimize explicitly within the model for what we want as interpretability. And that allows us to better articulate what the trade-off is.
Okay, that's actually very interesting because the second question that we had already kind of touches on something that you've addressed right now, which is when we're choosing an algorithm, should we focus more on the white box ones, the more explainable ones, and let's say neglect performance in exchange?
Yeah, I mean, this is an interesting question because I would suggest, what do you think of as a white box model? And what do you think of a black box model? And the truth is, all our models are probably somewhere in between. So a lot of interpretability is an intuition into the model behavior. And even black box models are not it's not like one day they'll become white box. It's more like we'll get progressively more nuance into their behavior. And that being said, I think that there'll always be some factors that determine the degree of comfort we have with the model without knowing everything, because we'll never know everything about our model. And what that means is there may be situations where, for example, you have a lot of historical data from the model. So let's say that you've deployed this model for 5 years, you're in an industrial setting, you've seen it scale to millions of people, and you have all those input outputs. You may have quite a bit of trust into that model, even if it's a black box model, because you've just seen enough input output combinations to have a good sense of what it's doing, even if you don't know exactly what the function is. However, if you're deploying a model for the first time, and you're about to push that, essentially like your code, submit your code, and you're wondering, oh my gosh, I hope this doesn't like completely do something odd when I deploy this at scale. You're probably going to really, really want to understand much more how the model is actually extracting features, because you have very limited historical data, and maybe your training data is actually very different from your deployment data. So this all impacts how we think about interpretability. But it's hard it's the most difficult thing I think about interpretability is when we talk about it as a binary objective. Things have to be interpretable or things don't have to be interpretable, because often it just depends on the circumstances, much like something like model compression. If you're operating in a resource constrained environment, it matters much more that you can have compression.
Okay, that's interesting, because I'm going to be a little bit autocratic here, but I have a question which is, it always bogged my mind a little bit, which is, does it, if you have a model that has a good output, should that be enough or not, even if you don't really understand deeply what's going on inside that model? Should the output be enough? I guess it's my question.
No. Slash maybe. So it depends on what you're trying to do. Let's say you're trying to predict, will my friend come visit me this weekend? Okay, so your model predicts yes. Maybe just trust it, because it's not a high stakes decision. And if your friend doesn't visit you, it's not the end of the world. But let's say you're trying to predict, will my cohort of friends, what's the likelihood that one will have a disease? That's a much more high stakes decision. And in that case, you just having a good output, and we frequently see this with deep neural networks, very, very confident predictions, so high probability that the model is very confident but completely incorrect. So a good example of this is that we have shown in research that if you just add noise to images, or a corruption, like you add high contrast, it completely throws the model. The model has no idea what to do with it, even though humans can see the difference and still distinguish. So that's where auditing is much more crucial. And it's kind of like any decision in our lives. Like humans, when we're deciding whether to go to one coffee shop or the other, normally we don't really beat ourselves up to like dissect why did we choose this coffee shop. But if we're deciding whether to take a job or a different job, we often try and force a lot of self-interpretability. We ponder why, we list the pros and the cons. And so it's the very same. Our emphasis on interpretability is really our emphasis on the stakes of what is the harm of a model getting an incorrect answer.
Okay. I think we could be rolling this for hours, but I want to drop my North Korea rib bone and look at what other people are asking. But by the way, a question that we have is, how do you compare having to interpret models that have non-visual tasks versus visual tasks? I assume visual tasks will be much more easy to understand.
Yes, this is an excellent question. So bravo to whoever asked it. I think this is an interesting question because the person who asked is completely correct. So visual tasks tend to be easier, and that's why so much interpretability research is focused on visual tasks, which I think is somewhat unfortunate, because things like audio and things like language have been more underserved. So there's been interesting work in language which has been trying to understand essentially gradient-based methods, so highlighting the words that matter. But in many ways, it's been the techniques have not transferred well, and I think that's mainly an issue of the attention of researchers. We need to spend more time thinking about other domains. That's really explains the emphasis on computer vision.
Okay, cool. Okay, I think I'm going to change the subject a little bit here. And another question we have is the current research. I'll just paraphrase. The current research on explainable AI is focused on post hoc explanation methods such as LIME and SHAP. What do you think about focusing on in-model interpretability? Example, trying to make a black box explain itself.
I love it. I think it's a research approach I'm really excited about, and I'll tell you why. Because our expectation that deep neural networks trained on cross entropy that have no constraint that they're interpretable, we're almost expecting that they arrive at the end of training, you've converged, and we're like, oh, I'm so disappointed it's not interpretable. But we never specified the constraint that it should be interpretable. So in some ways, our expectation at the end, and then doing all these acrobatics to make it interpretable, it's really interesting to think by the time the end of training has arrived, you have so few degrees of freedom. If we start earlier and we start thinking about what do we want to codify as what interpretability is, we have a lot more degrees of freedom to explore. And I just think it's a completely underserved area of research. I think it's very exciting. Good person, a good question from whoever asked it.
Yeah, no, I think this is a really, really interesting question, actually. I was trying to see if we get another one. We only have 1 minute left. Okay, let's do it like this. Let's lift up the veil on the geography question.
Excellent, good idea. Don't keep people waiting.
I'll take the floor. I'll let you go. What's the answer, Sarah?
So I believe you're referring to South Africa, Swaziland, and Lesotho. And Lesotho and Swaziland are two kingdoms within South Africa, so they're enclaves, but they're nation states. But they're also the one of the two remaining countries that have kings, which is kind of interesting.
Yes, yes.
So look it up. Fun facts.
They're right there with Spain and Denmark.
Yeah, yeah, true. You do know a lot about geography. Wow.
I have to confess, I have two passions. It's data science and geography, and sometimes I'm not sure which one I love the most.
Interesting.
I actually learned that Swaziland changed names recently, but I'm not sure which name did they take this time.
Oh, I'm not sure either. That's interesting.
I'm gonna post this somewhere in the platform if anybody is interested besides us two, and that's me.
Yeah.
Okay.
We may find it. No one else is.
Let me wrap
excellent.
this up because we're running out of time. Super interesting Q&A. At least it was for me. I think it was for everybody else too. Really interesting perspective that you brought to us.